Hello and welcome to the Armen Show podcast, science, people, creativity, learning more, expanding our framework, and interconnecting ideas we have spoken about in the past. On this one here, we have a wonderful guest in material that I always work on. I work with many students in math and science, notably math. Math has always been my thing for years and years: geometry, algebra, probability, trigonometry, and pre-calc, and even further. Our guest today is the author of The Story of Chance. What's luck got to do with it? We have Dr. Michael Orkin. Dr. Michael, welcome to the show.
Thanks, Armen. Happy to be here.
I'm glad to have you on. You're in the Berkeley region. Can you tell us a bit about your progression to where you are right now before we get into the book?
Sure. I came to Berkeley from the East Coast to go to college, and I wanted to be a math major, so I was. And then when I was a senior, I took a probability course, and the professor and I became sort of friendly, and he encouraged me to go to graduate school, so I did. And so I went in this Berkeley, UC Berkeley has its own statistics department. So that's where I went. I got a doctorate in statistics, and my thesis advisor was an expert in game theory. So that's what my topic was, game theory, in a very abstract way. But then when I got out into the world and I became an academic, a professor at one of the California State Universities, and then over the years I developed um, I had a lot of consulting work, and my consulting work is sort of an applied version of the probability and statistics that I learned in graduate school and also that I teach. Um, my particular area of consulting is um, how to decide between luck and skill. That's of use to people who are game developers who want to get in the app store these days, and there's a lot of that who want to have wagering in their games, and you can't do that um, without satisfying the certain regulations. And one of those regulations is that it be a game of skill, not a game of chance. That's partially a legal thing and a legal thing, not an illegal thing, and partially due to banks who don't like to have compulsive gamblers uh, going through them, and so having it a game of skill makes it um, a little more satisfying to the banks. So there's the banks, the app store, state and government regulators, stuff like that. They all need a report. So somehow it's just been determined over the last few years. There's been a proliferation of apps like FanDuel and DraftKings, I'm sure you've heard of, that have wagering on sports, but now the door is sort of open, and the way to get through that door is to prove that your game, your app, is a game of skill rather than a game of chance. And so the team that puts together a package to go through the various regulators in the app store and stuff to get their game online needs to have a report from someone like me saying that this is a game of skill. That's a statistical type of report. And so here I am. I'm teaching online right now at Berkeley City College. That's my other gig. I retired from Cal State and spend more time consulting. And I decided to write a book about some of these things because chance versus skill. What's the meaning of luck? Um, Things like that are all things that I deal with on a day-to-day basis in my consulting, and also I like to talk about that when I teach too.
When I think
So
of
here I am.
games, right? This is a wonderful thing.
Yeah.
When I think about games, I know somebody who very much enjoys various kinds of board games and games a lot. And is it fair to say that a good percentage of the most popular long-term games are of skill, and then some of the ones that are a bit more addictive on the phone are chance? Are there chance-based games that get very popular, or is that not really a thing?
Well, I think that the games of chance um, pretty are focused in the casinos and also in lottery. So if you go to a casino, you can play craps, you can play roulette, you can play keno, all games of chance. You can show mathematically there's no skill involved. I could be playing a dice game like craps for years, and someone who's never seen a pair of dice before can come in and do just as well as I can. Lottery is the perfect example, which is very popular in this country and in England as well. State lotteries, the Mega Millions lottery, which is a multi-state lottery, games of pure chance. So those are around, and a lot of people really enjoy them and get sort of hooked on them. And I could tell you stories of people who get in trouble for doing that. But of course, people get in trouble for playing games of skill too. But games of skill, sports betting or sports wagering is considered sort of a game of skill at this point. Um, and the federal law against it has been relaxed. And now you just have to say, many states say it's fine, but generally um, you have to show that it's a game of skill. And I mean, the way I do that is to look at player data and show that some players do better than they could just by being lucky. So that's how luck is involved. But it is fair to say that there are a lot of people who get sort of addicted to games of chance and to games of with some skill.
How does one place skill into a game numerically? What does that involve? How do you make it
Oh,
so
okay.
it's skill based?
So yeah, so the basic idea. So first of all, there's some games that no one's going to argue with, like chess or checkers or um, other games of that nature, bowling, physical games, not betting on bowling, but just bowling, are games of skill. But for me, I mean, those aren't app games, and although you can play chess online, um, but the basic idea is to look at some data of players and how they did, and so whether it's playing for free or playing for money, I'll get a spreadsheet or some kind of a database that shows how well players did. And I have to show, so basic way to do this is to show that there are some players who play this game who do better than chance would allow. And you have to use a statistical test, sometimes called the hypothesis test, which you're probably familiar with. Um, but or sometimes called a significance test. And so the idea is to show that there are players who do significantly better than luck would allow. And you use something called a p-value to show that. And you can never, with statistics, you can never say anything for certain, although you can say for certain that craps is a game of chance. But in this case, in the case of a game of skill, you just show that there are some players, a significant number of players who are doing better than they could just by being lucky. So when you think about that for a minute, you have to say, well, wait a minute, what if somebody just plays once? You can't tell. And that's true. So I have to look at some data where we have players who played a number of times.
That's one of my favorite things about the category of probability is that it lends itself to more or longer term or more data, a larger set, and that is most of what our existence is. It's a longer set. It's not just a one-time
Right.
thing generally.
Yeah.
So I like that element of it. And also makes you think in terms of longer term decisions. It's almost like having a sense of probability will lead to a better sense of life because life isn't just an hour, for example, or just a moment, a
Right.
brief
Well,
moment.
that's a very interesting comment, and I completely agree. And it's interesting because you can go beyond that. I'll give you an example. What's the probability of a big earthquake hitting California sometime in the next year? Well, that's a difficult question in probability because it's not something that happens very often. And computing probabilities generally depends on looking at how things occur over time. You can use the law of averages and stuff like that. And as you say, you have to look at you can't just look at what happens in the next hour. But there are some events that are so rare, like a major earthquake, that it's very difficult to compute a probability. In fact, a friend of mine, Philip Stark at UC Berkeley, wrote a paper a few years ago with someone else on how do you predict what the chances of a big earthquake hitting California sometime in the next year. And the answer is, well, you can't do that very well. So the probability has its own sort of sphere of computation, which is, roughly speaking, our lifetime. And if you go beyond that, it gets difficult because you don't have any evidence, any data. Um,
Two things come to mind. One I'll follow up with after, but one is that I have a sense that the individuals who really understand probabilities are at the top of our society because if you look at economics or uh, we're not so far away from being prediction oriented people or organisms, and having a sense of that in the bigger picture is going to make you super smooth for a long time. Or insurance companies, the way they take that into account in terms of how much to charge and how that's going to last over 10, 20, 30 years. Is it fair to say that having a superb sense of probability may put you in the upper echelon of understanding what all people are going to do?
well, I think that that helps. I think you need to have a bunch of other uh, things have to fall in place. You have to be experienced in various things. And of course, things are very specialized these days. So you have to be good in what your specialty is. Now, I'm glad you mentioned insurance companies because there's one big thing that's still kind of interesting, in which I've had a few clients. I'll give you one brief story. I had a client who was basically, I was working for the lawyer of this person who was working for a very large company, and the company's insurance, and the company was had thousands of employees. Some worked at desk jobs, and this person worked an outside job, um, doing things that were sort of risky. And the insurance wing of the company or their insurance company said, this person's accident prone. So that's a big deal with insurance companies. How do you tell if someone's accident prone? Well, right now, there's a lot of, uh, there have been hundreds of papers written on what does it mean to be accident prone recently. And the latest version of it is you have a predisposition for accidents. Well, what does that mean? Well, it's not clear. But one thing is clear, and that is you shouldn't fire someone from a job because they're unlucky. And this person was unlucky. She had um, more accidents than average. And that's what the company was saying. Well, she had more accidents than average, therefore she's accident prone. Well, you have to do more than that. And the more than that means it's the same as the difference between luck and skill, but the reverse. You have to show that this person is having more accidents than just being unlucky, because it isn't fair to fire somebody just because they're unlucky. So we presented that and got to a mediator, and the company completely caved in because their statistician was using this definition of accident prone as just being unlucky. And so she got her job back. This was a number of years ago. She's still working at the company. She got promoted. So anyway, that brings up this other version of the same thing. To tell if someone's accident prone, at the very least, you have to show that they're doing worse than just bad luck. So insurance companies pay a lot of attention to this.
This is true. It's important to take into account not just like a first layer of understanding what's happening, but then, oh, okay, there may be some luck involved. We need to account for
Yeah.
that. There's multiple layers to this.
Yep.
One huge thing that came to mind while I was reading your book is that there's areas where statistics and probability is my favorite thing to see in a lot of research papers. It makes the papers right on point. The data is well represented. I understand it completely. I'm very logical and science minded, so that's my category of interest. And then what I see a lot of on the internet is so much either non-use of probability and statistics, or it almost seems like an avoidance of it. Like, oh, those are statistics, but we don't work with that. I see that way more often than I actually see people using the data, well, which some people do. Is there some reasoning that comes to mind of why there is such an avoidance of it in the general public, as though it's a separate thing, even though those statistics include those individuals talking about that
Yeah.
as whatever they're doing in their life
Well, for
in it?
one thing, there's so much data out there now that people are generally just afraid to say, oh, if I try to really understand this, I'm going to have to spend a huge amount of time. So that just we're overloaded with data, and that's something that's going to get worse because of all the AI things that are coming online right now. Just more sources of data. So some people, in fact, I would say it's sort of natural unless that's your field, to sort of shy away from huge amounts of data. Also, there's this big thing right now, like in politics, each side keeps accusing the other of, and I don't want to get political, but each side is accusing the other of misinformation and of misrepresenting data, and it's a big issue. Um, Donald Trump, and this is not either for or against him, but he likes to say that he does things based on his hunches and his belief without having to pour over data. And some people are very good at that. So I don't know whether he is or not, but that's another thing that some people do. They get good at estimating things without having to read tons of research papers before they make a decision. But of course, that can get you in trouble too.
It's true. One thing that is popular in the field of statistics is causation versus correlation, the value of each. How much can a correlation tell you? How far can it go about informing you about something, kind of like a causation? Or can it not reach that far
Well,
over?
so that's a very good question. It's something I talk about in the book, and that is this. So first, there's a basic rule: correlation. If two things are correlated, does not mean causation, because correlations are usually based on observational data, which means there's lots of other stuff going on in the background. That doesn't mean that because two things are correlated, there isn't causation. It just means you haven't proved causation. So there's one example that I give, and that is there was some research when the polio vaccine was being developed in the late 1950s. A researcher discovered that when people drank lots of cola, lots of Cokes, polio incidence went up. When soft drink sales go up, so there's a very strong positive correlation between soft drink sales and polio incidence. There really was such a correlation. And so people started saying, oh, now we've discovered the cause, notice the word cause, of polio. And further digging showed that there was no causation at all. The fact was that it was the weather in the background that was causing both things to move. Warm weather, people drink more sodas when the weather's warm. And also the polio virus gets more active when the weather's warm. So there's no correlation between drinking cola, drinking soft drinks, same thing, and polio. But there's no causation there, but there is correlation. So that's an example on that side. But people do, when they see a correlation, it can be useful as a marker. Like you could learn something from it. For instance, people learned sort of as a result of that more about the polio virus getting more active in warm weather. Um, and there are, but in order to establish causation, you have to do a little bit more. It doesn't mean that you don't have causation. It just means you have to do a little bit more to show causation. You have to have controlled experiments where you can randomly assign people, for example, to a control group, an experimental group, and then you can sort of weed out, you sort of factor out the background stuff because you have random assignment. And then you can start talking about causation. Um, there's another example that's a little more complicated, so I'll just mention it briefly, and that is the Federal Reserve. I mentioned this in my book too. The Federal Reserve is in charge of raising or lowering interest rates. And there's something called the Phillips curve, which is based on some 19th century employment data that shows a correlation between employment and inflation. And so people still use that. It's been shown that this curve, that you can't use 19th century economic data and apply it to the 2020s, but they still have been, um, let's say, relying on that curve to decide whether to raise interest rates, because the idea is if interest rates go up, then unemployment goes up, and then by the Phillips curve, inflation goes down. But none of that works, it turns out, because as interest rates go up, when I say none of it works, I mean in the current situation, the current economic situation, when unemployment goes up, when interest rates go up, which is what the Federal Reserve has been doing for the last few years, they finally started to lower rates. Unemployment did not go up. Employment stayed strong, and inflation did not go down. And so that wasn't the only thing, but one of the bases, which most economists now think is not very useful, in fact useless, was using this thing called the Phillips curve, in which you're taking this correlation that was discovered and saying this is, and using it to try to adjust interest rates to cause something. And so, again, correlation doesn't necessarily mean causation.
That's the important point you bring up at the end there of knowing what you're doing and what it's causing.
Yeah,
Because if you don't make the right links, then you are doing something that may have no connection to those items. And it's not affecting it because it has no direct connection. And
that's
so
right. That's right.
that is a nonsensical effort. So in a way, having a direct connection or understanding what the direct connection is a way to become efficient versus throwing around extra
And there's
energy or
certainly a
money.
lot of data around. You don't have to rely on 19th century English unemployment data or inflation data in order to find stuff out.
This is true. Another realm of statistics and or probability is Bayes' rule, and I once spoke with butterfly researcher Susan Finkbeiner at Cal State Long Beach. She does butterfly work and
Yeah.
analyzes their whole life and their paths and what they do, and uses a lot of Bayesian reasoning. Can you tell us about Bayes' rule and what it is good for?
Yeah, so Bayes' rule was developed by a 17th century minister named Bayes, Thomas Bayes, I think his name was. And he was interested in conditional probability, which talks about how you can use information to update your knowledge of things. And for instance, if you deal from a deck of cards, you have conditional probability. The probability, if I deal a card out, it's an ace, I know then, since there are only 51 cards left and only three aces, the chance that I'll get an ace on the second draw is 3 out of 51. If my first card is not an ace, the chance is 4 out of 51 that the next card is an ace. That's called conditional probability. Well, you can use that and get a little more sophisticated to find a rule that tells you how to update probability, your initial or prior probabilities, based on some knowledge that you get in the meantime. So you have some prior probabilities, you do an experiment or do something that causes you to be able to update those prior probabilities, but you use conditional probability based on what you've done. And Bayes' rule lets you put it all into a nice formula. And I'll give you an example. Diagnostic test for TB. Anyone who works in California for the school system has to take a TB test, because TB, although not very common in this state, is very contagious. And so nobody wants to take any chances. So they developed a diagnostic test, which is the scratch off skin test, which you may have taken before. A lot of people have taken it. If you get a rash, then that means, well, you've been exposed at some point to TB, or you get somehow a positive reaction. So you have to do something else, like get a chest x-ray. If you don't get any reaction to the skin test, then you're clear. You don't have to go any further. So that the result of the skin test changes the probability that you have TB. You start out with just the prior probability, the percentage you have it in the whole state, which is very low. When I say state, I mean, you can do this anywhere, but state of California is what I'm familiar with. So the diagnostic test, you can use Bayes' rule to update the probability of just the percentage of people in the state who have this disease. So this is a diagnostic test for any rare disease, will work the same way mathematically. And so my chance of having it might go as a result of this test from 1% up to 20%. It still doesn't mean I have the disease. If I get a positive reaction, I have to go get a chest x-ray in the case of TB. But it's the way to keep track of these conditional probabilities. Now, I'll give you one more example, and the reason is because it seems like it's completely different. And that is with this idea, with this thing called resemblance stereotyping. So Daniel Kahneman wrote a book called Thinking, Fast and Slow. I don't know if you're familiar with that book.
Wonderful book.
Yeah, wonderful book. Right. Good. Daniel Kahneman was a Nobel Prize winning psychologist, but he sort of specialized in doing these experiments to try to show things, and he would use Bayes' rule and things like that. He taught at various places. He ended up at Berkeley for a couple of years, passed away recently. So anyway, here's the experiment from the very first part of his book, and he would give these sort of experiments to his graduate students. So the idea is you see somebody who's very shy and has a bunch of other characteristics. Let's just say he's very shy. And the question is, given that information, is this person a librarian or a farmer? His name is Steve in Kahneman's book. Is he a librarian or a farmer, given that information that you see a shy person who's very reserved, is very meticulous? Is he a librarian or a farmer? So most of Kahneman's graduate students said, well, it sounds like a librarian. And that's called resemblance stereotyping because he resembles a librarian. But you can use Bayes' rule to find that, well, you don't have to go through all the computations. Turns out that there are 20 times more farmers than there are librarians out there in the population. So just because you see someone who, given that they're a librarian, may be more likely to be shy than given that they're a farmer, doesn't matter if there are a lot more farmers out there. So it's the same math problem as the diagnostic test for the rare disease. Just because there are so many more farmers, you can use Bayes' rule to show that the probability that the shy person is a librarian is much lower than the probability that they're a farmer. So those are two examples of the same thing.
I like that second example there. It gets your mind in the right mode of thinking to process something.
Yeah.
Two things come to mind from that. One of them, I once messaged Daniel Kahneman about his book and how I thought it was swell, and he mentioned he had done so many interviews on it, and he was done with interviews on it, but he was very glad about having written it, so that was cool. And then
he would sort of go on tour towards the end of his life in his mid 80s. He went on tour with Nicholas Taleb, who wrote The Black Swan, and they were sort of oppose each other in these sort of debates that were very popular. They're on YouTube, some of them. You can see them. Very interesting.
Nicholas is a very punchy character. I like his style. He's very
smart guy.
Yes. Now, and then the other point that came to mind, you talked about changing probabilities earlier. It made me think about games. Do they do that in games, whether computer games or I don't know how it would work in board games, but where probabilities change during the game to make it harder? So the probability of something happening was a certain percentage earlier in the game, and then later in the game it's much lower. So even if you put the same amount of effort, you'll have a lower chance of getting that result. Would they do something like that in a game?
Yeah, in fact, there's the very first example of that was the use of simulation done by IBM computer programmers in the late 1950s to try to find winning strategies for blackjack. And of course, blackjack is a game with cards, and so the probabilities change as you go through the deck as more cards are dealt. And they discovered that doing these Monte Carlo computer simulations, which had previously just been used for defense purposes or handling very intractable physics problems. They found that the player who keeps track of the cards in a certain way can have an advantage in blackjack. And Ed Thorpe in 1962 was a math professor at UC Irvine, wrote a book called Beat the Dealer. This is 1962. That's still in print. And many, many books have been spawned as a result of that. And he shows a way that you can keep track of the cards. You don't have to memorize each card as it's dealt out, but keep track of like high value, low value cards. And as the cards get dealt out of the deck, then what happens is one of the things that can happen is what you just mentioned. Things can get much worse. The chance of you winning gets lower, but also things can get much better. And so if you keep track of the cards, you'll know which is which, and you know when you have an advantage over the dealer. And of course, as a result of that book, the casinos decided, well, we'll take care of that. We'll just shuffle after every hand. Then you can keep track of all the cards you want, but it doesn't matter because you get a new deck every time you play a hand. But still, you can still get decks, you can still get games where cards are dealt somewhat out of the deck until the deck is low. But that's a good example of how conditional probabilities can help you win a game.
Your commentary there on Monte Carlo simulations reminded me, that was one of my favorite topics. I did biochemistry a long time ago, and we used that a few times for papers. And I like that you would go to a local minima, and it's like you'd fall into,
Yeah.
that's where the data lends itself to. Do we use that in various fields? I'm thinking maybe traffic, like, oh, there's like a local area where that's where the most accidents happen, or people are most likely to, it's like you fall into, I think about it as a metaphor for life too, whereas if you fall into a local minimum of comfortability, you're likely to stay there unless you can somehow make the hump up to the other part using activation energy. But where is Monte Carlo simulation used today, or what comes to mind when you think of that?
Well, there are a few things that, first of all, Monte Carlo simulation was originally invented by a mathematician named Stanislas Ulam back in the 50s, the late 40s, early 50s, and to try to figure out physics problems related to development of thermonuclear weapons. And then over the years started being used by others, such as developing blackjack. And now here's an example of the weather. So the weather is very hard to predict. In fact, it's impossible to predict far in advance. I'm not talking about the climate, I'm talking about the weather, which is more localized stuff. But now when you get a weather forecast that says there's a 60% chance that it'll rain tomorrow, what does that mean? Well, what it usually means is that the meteorology department of the newscast or whoever has done Monte Carlo simulations of various weather scenarios and has found that in 60% of those simulations, it rains the next day. So Monte Carlo simulations are now used very much in weather forecasting and in other types of forecasting. In statistics, it's become very popular in an abstract way. There's a whole programming language called R, just the letter R, which is popular among statisticians because it allows you to do simulations very quickly. Not with a huge amount of data maybe, but it's a very powerful language. But the thing that first came to my mind is weather forecasting for how Monte Carlo simulation is used outside the gaming world. I guess you consider the weather a game in a way.
That is true. Like the hurricane simulations that have been super detailed and whatnot. How much of statistician work behind the scenes gets out to the public directly, or is it usually behind the scenes and then something's created and then the public interacts with this thing and not the actual, is the actual processing ever seen by the public or not so much?
Not so much, I think, but right now there's this, and over the last, say, 10 years, there's been this big sort of paradigm shift about being a statistician and being a data scientist. And the looking at they call it big data, has sort of filtered into mainstream computer science now, especially with the development of AI. But this started before AI. Well, I mean, it started before the new version of AI. And so now, for example, I teach online at Berkeley City College, and it's part of a community college district in Berkeley and Oakland, California. And they're introducing data science courses in the statistics or math departments. I'm in a math department. And this is brand new. It's how do we get, because of course these things all happen because of jobs and what's available for students when they graduate. And data science, as it's now called, has become sort of an up-and-coming job category. And so they're starting to offer courses in it. UC Berkeley is starting to offer courses in it too. So I see. So your question was about what do the most people on the street look under the hood at all the statistical stuff. And so the answer is that I don't think that's necessarily the case, but there's a lot more interest now in analyzing data. And that interest is coming from the computer people.
What does the average person what could the average person most benefit from knowing about probability and statistics that they don't currently tend to?
Well, that's a really good question. It's one that I ask myself. So I'll give you my opinion on a couple of things. One, I think people don't understand, everybody, not just non-technical people, but even technical people, don't understand, can't really comprehend intuitively rare events, very low probabilities. So, for example, the Mega Millions, and I talk about this in my book, I have a couple of chapters, in fact. The Mega Millions lottery. Everybody knows about that. People play the lottery. It's a game of chance, but it's a fun game for some people. And your chance of winning the Mega Millions, it's a multi-state game, so you can play it in most states in this country. And of course, there's Powerball. England has its own lotteries. Lotteries, historically, the word lot comes from land, and lotteries were a way to randomly assign land to people, like 1,000 years ago. Anyway, the Mega Millions lottery has various prizes, but the chance of winning the jackpot, that means all the numbers you pick are the winning numbers, is about 1 in 303 million. And so people don't understand what that means. So I'll give you a couple of analogies. If you buy 50 Mega Millions tickets a week, you win the Mega Millions jackpot on the average of once every 116,000 years. If you have to drive a mile every time you buy a Mega Millions ticket, then you'll drive an average of 633 round trips to the moon before you win the jackpot on the average. One final analogy. Let's say you know one person in Canada. You put everybody's name and everybody in Canada's name on pieces of paper and put them in a big box. Okay? And there's one person in that big box that you know. So let's say you draw a name at random from that box, and let's say you buy a lottery ticket. So you're 9 times more likely to pick your friend's name out of that box than you are to win the jackpot. So these are sort of sobering analogies, but a question arises. And the question is, if it's so unlikely that you'll win the lottery jackpot, how come there are winners? So this is a very basic question in probability when you're studying rare events. And the reason, not super complicated, you don't have to know any math, but you have to be intuitive. The reason, there are winners about every week or two. Maybe, sometimes there aren't winners for a few weeks. Then the jackpot piles up and more people buy tickets, and then there's a winner. The reason there are jackpot winners for the Mega Millions lottery is because so many tickets are sold. And there's a mathematical principle to that. which is um, given enough opportunity, in this case, tickets sold, then any weird thing will happen just due to chance. And that's something that most people haven't thought that much about or don't realize, but that explains all kinds of things like weird coincidences, um, weird happenings. I just ran into my brother. I haven't seen him in 20 years, in a coffee shop in Berkeley. What's going on? And so, and people over the years, like Carl Jung, the famous psychiatrist of the 20th century, even had a term for that, rare events that involve more than one thing happening at once. And he called that synchronicity. And synchronicity was Jung's definition of something that involves like weird things happening, more than one thing. Something that's in between chance and causality. And so that's how much people pay attention to such things. Now, it turns out that Jung is probably wrong. Namely, every example that he gives, and I can give some of those examples, but the basic idea is every example that he gives can be explained by chance and just by this idea that weird things will happen given enough opportunity. You don't see the background. For every Mega Millions winner, there are about 300 million losers, and you don't pay attention to the losers. There was a very popular news article a few years ago about, I think it was in England or somewhere. Anyway, this octopus had predicted 14 soccer matches in a row. And so, how could this octopus do that? And it's very unlikely that that would happen if someone's just tossing a coin to predict the result of a soccer match. And these were like playoff matches. And so it turned out that this background was also an event. There are lots of animals that are used for promotion to predict the results of sporting events. In fact, in Las Vegas, there was this, I think it was a hamster at the Rio Hotel that was picking football games. And so you have enough of these, and it's sort of fake because the typical way to do it is to put two food bowls, one for each team, and then see which food bowl the animal goes to. But the point is that even without all the other things you can think of, given enough opportunity, there will be these weird events. Not to mention the fact that randomness itself has streaks. So if you have enough people participating or enough animals participating, one of them will have a streak, a lucky streak. So I think that's an important thing.
This is a big one to me. Having clarity of what a probability actually is, to me, is a huge sign of intelligence. Because you're seeing what actually is versus kind of you're off. There's like a hope-based thing, but it's kind of
people have bad intuitions when it comes to things like that. Mathematicians included.
That's funny. My last question is, are there any people in your path that have been a fork in your road that led you to where you are today, or any notable figures that come to mind that it's like, oh, that person, if it wasn't for that person, I wouldn't have gone in that direction, anything like that?
Yeah, that's a good question. So I'll go back to my graduate school days. I mentioned earlier that for my first probability course, which I took as an undergraduate, a senior math major, was that professor was influential because he got me to go to statistics. I'd never thought about that before. I was going to just continue in the math game and, as I mentioned, go on to work for some tech company. And then when I was in graduate school, the person who got me interested in games and thinking about things as games was my graduate advisor, a guy named David Blackwell, who passed away a few years ago. But he was very influential, probably one of the most influential people in my life because he was this very sort of quiet person, but when you could ask him any question in math, and he would find a way to turn it into something like a game and give it figure out an answer. Now that wasn't obviously wasn't true for anything, but he was better at it and very inspiring to me. And then over the years, I did I did a bunch of work. I met this guy who was the head odds maker in Las Vegas a number of years ago on a TV show. We were talking about computerizing sports stuff, sports data, and it was a show in San Jose, California, called the Computer Chronicles. I don't think it exists anymore, but so this guy we became fast friends, and then I got into the whole Las Vegas world, helping him. His name is Roxy Roxborough. He's retired now, but he's the person credited for computerizing odds making in Las Vegas. So he was influential because he got me interested in sports betting and odds for sports betting. So those are some of my main professional inspirations or influences.
That is wonderful. Actually, I forgot this one here. If you had a megaphone and you were able to say one sentence to all people about probability and statistics you would want them to know, what might be a takeaway they would want that would be helpful for them to hear?
Okay, that's you caught me on that one. I don't have a canned answer for you, but I guess I would say one of the things I would say. I'd say I have a bunch of things, but one of the things I would say is what I was just saying a few minutes ago. Given enough opportunity, any weird thing will happen just due to chance. I would say that. And then if I had to get into some other things, I would say something like this. We haven't talked about this. I would say just because you have a winning game doesn't mean you're going to win, because you have to be able to manage your money. So that's another thing from my field that's important. I can talk about that. I have a chapter in my book on Sam Bankman-Fried, SBF, who everybody knows had an untimely demise and is now sitting in prison in New York. But one of the reasons is that he was a very smart guy and knew math. He went to MIT, he majored in math and physics. He learned about positive expected value, which is positive average value if you keep playing the game over and over. And he used that. There was a book by a guy who interviewed him a lot in which he kept talking about positive expected value, positive expected value. He would always spot these bets in the crypto world that had positive expected value. But if you have positive expected value and bet all your money each time, you're going to quickly go broke, because there's randomness in just about everything. If I am the world's greatest blackjack player, I'm only going to bet a small fraction of my bankroll on each hand, because if I keep betting everything, I'm going to have a bad hand and lose everything. And so when that started happening to him, rather than start learning about money management, which is sort of a stuffy sounding term, he started borrowing from his investors. He had two companies, the crypto exchange and his hedge fund, and he would start borrowing from his investors to make bigger and bigger bets. He had the right idea, but he didn't know about managing his money, and you can't borrow money from people who don't know that you're doing that. So that's a good example. That's another thing I would talk about to someone is don't get overconfident just because you are smart and see a winning opportunity. You have to still be careful, and that sort of brings up another thing I guess I would say, and that is let's see, how would I put it? So it's okay to screw up from time to time. Just don't do anything really stupid. And that's what Sam Bankman-Fried did. He started getting ahead of himself. And so that was actually proved mathematically by my thesis advisor many years ago, that sort of simple sounding comment, just it's okay to make mistakes. Just don't do anything stupid. He actually wrote a mathematics paper on that. So that's another thing.
That's an important one right there. Little errors in trying things.
Yeah,
It's fine,
exactly.
but some huge loss of some sort we want to avoid that if possible. Dr. Michael Orkin, I would like to thank you for having joined on this episode, describing a bit from the story of chance, what's luck got to do with it, representing for the region of Berkeley, which is one of my favorite areas, and San Leandro and the East Bay and parts of San Francisco, and bringing us knowledge on statistics and probability. Glad to have you on the program.
My pleasure, Armen. It was good to be on your show.
Glad to have you on, and we are out.